Right now, as you are reading this, you are moving through something you cannot see, cannot touch, and cannot step outside of. It has no color. It makes no sound. It does not announce itself when it bends, when it stretches, or when it slows the passage of moments around a massive object. You have spent your entire life inside it. Every breath you have ever taken, every thought you have ever had, every second that has passed since the moment you were born, all of it has happened within a structure so fundamental, so completely woven into the fabric of existence that most people never stop to ask what it actually is. Right now, the nearest star beyond our sun sits at a distance so vast that if you traveled toward it at the speed of a commercial aircraft, you would need approximately 5 million years to arrive. The light leaving that star tonight will take 4 years to reach your eyes. 4 years of uninterrupted travel at 186,000 miles per second. That is how far away the closest thing is. And yet, across that entire journey, across every one of those light years of emptiness, something holds. Something shapes the path that light follows. Something ensures that the physics operating near that distant star obeys the same rules as the physics operating in the room where you are sitting right now. That something is not matter. It is not energy in the conventional sense. It is the structure that contains both. But here is what most people get wrong. When they hear the word spacetime, they picture a kind of invisible container, a vast, featureless room in which stars and planets float like objects on a shelf. They imagine that space is simply the emptiness between things and that time is simply the clock ticking on the wall. They imagine that these two concepts are separate, parallel, perhaps related, but ultimately independent of one another. And that picture, intuitive as it feels, is not just incomplete. It is fundamentally, profoundly wrong. Space and time are not two things that happen to coexist. They are one thing. A single interwoven structure that bends, stretches, curves, and responds to everything within it. A structure that is right now actively shaping every event unfolding across the entire observable universe. And despite more than a century of extraordinary scientific progress, despite the most precise instruments ever built, despite mathematics of breathtaking elegance and experimental confirmation after experimental confirmation, we still do not fully understand what that structure actually is. That is the question at the heart of what you are about to explore. Not the easy version of the question, not the version that gets answered with a diagram of a rubber sheet and a bowling ball. The real version. The version that keeps some of the most brilliant minds in human history awake at night, turning over paradoxes that refuse to resolve, staring at equations that work perfectly until the moment they catastrophically do not. Why, after more than 100 years, does space-time remain one of the deepest unsolved mysteries in all of science? Why do our two greatest theories of physical reality, theories that have been tested to extraordinary precision, theories that have predicted phenomena before we had the instruments to detect them, why do these two theories, when placed side by side, simply refuse to cooperate? And what does that refusal tell us about the true nature of the stage on which the universe performs? If you find yourself drawn to questions that do not have clean answers, to ideas that stretch the edges of what is knowable, to journeys that leave you looking at ordinary things in permanently altered ways, do something small for this channel. Hit the like button, subscribe. It costs nothing, and it allows this kind of exploration to keep reaching people who need it. Now make yourself comfortable. Settle in, because what follows is not a simple story. It is one of the strangest, most humbling, most quietly devastating intellectual journeys that physics has ever taken. And it begins, as so many things do, with something that seems obvious. Let's begin. The first thing to understand is that the way you experience the world is not the way the world actually is. This is not a philosophical provocation. It is a measurable, experimentally confirmed fact. Your brain evolved over millions of years to navigate a very specific kind of environment. Solid surfaces, moderate speeds, predictable distances, the kind of world where objects stay, where you put them, where time moves at a steady rhythm, and where the space between 2 points remains fixed regardless of who is measuring it. That world, the world of everyday human experience, operates under rules that feel self-evident precisely because they work so reliably at the scales we inhabit. Drop an object, it falls. Throw something forward while running. It moves faster relative to the ground than if you threw it while standing still. Two events either happen at the same time, or they do not. These seem like the rules of reality itself. They are not. They are approximations. They are what the deeper rules look like when you observe them from the limited, slow-moving, moderately gravitational vantage point of a human being on the surface of a medium-sized planet. The moment you step outside those conditions, the moment you move fast enough or get close enough to something sufficiently massive, the familiar rules begin to soften, then to bend, and finally to break. Not because the universe becomes chaotic, but because the universe was never as simple as it appeared from where we were standing. The story of how humanity discovered this begins not with a dramatic experiment or a sudden revelation, but with a nagging inconsistency in the mathematics. By the late 19th century, physicists had two extraordinarily successful frameworks for understanding the world. The first was Newtonian mechanics, the elegant set of laws describing how objects move, how forces act, how planets orbit. It had been verified across 2 centuries of observation. It predicted the existence of Neptune before anyone had seen it simply by calculating the gravitational influence it had to be exerting on Uranus. It was by any reasonable standard one of the greatest intellectual achievements in human history. The second framework was the theory of electromagnetism, developed largely by James Clerk Maxwell. Maxwell's equations described how electric and magnetic fields behave and propagate, and they contained within them a prediction that would quietly detonate the foundations of classical physics. They predicted the speed of light, not as an observation but as a mathematical consequence. Light, Maxwell showed, was an electromagnetic wave, and that wave traveled at a specific fixed velocity, approximately 186,000 miles per second. The problem was this: Maxwell's equation said nothing about what that speed was measured relative to. In Newtonian mechanics, speed is always relative to something. A train moves at 60 miles per hour relative to the ground. A ball thrown forward on that train moves at 60 miles per hour, plus the speed of the throw relative to the ground. Speed adds. Speed subtracts. Speed depends on your reference frame, but the speed of light embedded in Maxwell's equations appeared to be absolute. It was just a number, a constant, with no reference frame attached. For years, physicists assumed there must be a medium through which light traveled, something called the luminiferous ether, an invisible substance filling all of space. If such a medium existed, then the speed of light would be fixed relative to the ether, and observers moving through the ether at different speeds would measure different speeds of light. That would restore the familiar Newtonian logic. In 1887, Albert Michelson and Edward Morley conducted an extraordinarily precise experiment designed to detect Earth's motion through this ether. If the ether existed, then as Earth orbited the Sun, it would move through the ether at different velocities at different times of year. Light traveling in the direction of Earth's motion should travel at a slightly different speed than light traveling perpendicular to it. The experiment found no difference whatsoever. None. The speed of light was the same in every direction regardless of how Earth was moving. The ether did not exist, and in the absence of the ether, the speed of light was simply always everywhere for every observer regardless of their motion the same. This result was not just puzzling, it was structurally catastrophic for the Newtonian picture of reality. If light always travels at the same speed regardless of how you are moving, then the familiar rule of adding velocities cannot apply to light. And if that rule fails for light, something else must give instead. Something must adjust to ensure that every observer, regardless of their motion, measures the same speed of light. That something turned out to be space and time themselves. Into this crisis stepped a 26-year-old patent clerk in Bern, Switzerland in 1905. Albert Einstein had no laboratory, he had no telescope, no particle accelerator, no institutional resources. What he had was an unusual willingness to follow the logic of a question all the way to its conclusion, regardless of how uncomfortable that conclusion became. Einstein asked himself a simple question: what would the world look like if you were riding alongside a beam of light? And in sitting with that question long enough, he arrived at an answer that restructured everything. If the speed of light is constant for all observers, Einstein realized, then space and time cannot be constant. They must adjust. When you move faster, time slows down for you relative to a stationary observer. When you move faster distances in the direction of your motion contract, these are not illusions, they are not measurement errors. They are the actual physical behavior of space and time in a universe where the speed of light is fixed. Space and time are not separate, independent things. They are two aspects of a single unified structure, and that structure bends, stretches, and shifts depending on motion and, as Einstein would later show, on gravity. This is the moment the familiar picture of reality begins to dissolve. Because once you accept that time can slow down, not metaphorically, not in some psychological sense, but literally, physically, measurably, then the universe you thought you understood becomes something stranger. Consider what this means in practice. Two identical atomic clocks synchronized perfectly. Place one at sea level, the other at the top of a mountain. Let them run for a year. Bring them back together. The clock that spent the year closer to Earth's massive gravitational field will have ticked slightly fewer times, not because anything went wrong with it, because time itself ran more slowly in the deeper gravitational well. This has been measured. It is not a theoretical curiosity. It is the reason the GPS system in your phone requires constant correction. The satellites orbiting high above Earth, farther from its gravitational pull and moving at orbital speeds, experience time differently than the clocks on the ground. Without accounting for this difference, the positional errors would accumulate at a rate of roughly 7 miles per day. Every time you navigate somewhere using a map on your phone, you are depending on the fact that time runs at different rates in different parts of space-time. You are, in a very real sense, holding the consequences of relativity in your hand. But the deeper question, the question that will follow us through everything that comes next, is not whether space-time bends. That is established. It bends. It is not even how space-time bends. Einstein's equations describe that with extraordinary precision. The question is, what space-time actually is. When it bends, what is doing the bending? When it stretches, what is being stretched? When gravity curves the path of a planet or slows the ticking of a clock, what is the underlying nature of the thing being shaped? This is where certainty ends. This is where the equations, beautiful and powerful as they are, become silent. And this silence is not a small gap in our knowledge, a missing detail to be filled in by the next generation of experiments. It is a chasm, a fundamental incompleteness at the very foundation of our understanding of physical reality. To sense how deep that chasm is, consider a simple image. Imagine standing in a room and being told that everything you see, the floor, the walls, the ceiling, the space between your fingers, is not the bottom layer of reality. It is an emergent property, a behavior that arises from something else, something smaller, something more fundamental, something that does not look like space at all. Imagine being told that the 3 dimensions you move through, the duration you experience as the passage of moments, the geometry that allows you to say that one object is farther away than another, all of it might be a kind of large-scale average, a smooth appearance that conceals a much stranger truth beneath. That possibility is not fringe speculation. It is one of the serious directions in which fundamental physics is currently moving. And to understand why, we need to go further. We need to look at what happens when the 2 greatest theories in the history of science meet each other face to face and find that they have nothing to say to one another. But that comes next. There is a particular kind of frustration that comes from understanding something intellectually while being completely unable to feel it intuitively. You can read the words, you can follow the logic, you can nod along as each step leads to the next. And yet somewhere beneath the surface of comprehension, something refuses to settle. The idea remains slippery. It sits in your mind without weight, without texture, without the sense of having truly landed. This is the experience that almost every person has when they encounter space-time for the first time, and the second time, and often the 10th. It is not a failure of intelligence. It is not a sign that the explanation was unclear. It is something more fundamental than either of those things. It is the natural consequence of trying to use a mind shaped by millions of years of evolution on a problem that evolution never prepared it to solve. Think about what your brain was actually built for, not what it is capable of with effort and education, but what it was optimized to do through the long, slow pressure of natural selection. Your ancestors survived because they could judge distances accurately enough to hunt and avoid being hunted. They could anticipate the trajectories of thrown objects. They could navigate terrain, remember the locations of resources, recognize faces, detect threats. They needed to understand a world of moderate speeds, stable surfaces, and consistent distances. A world where time moved at a single reliable rate, where space did not stretch or compress, where the rules that worked yesterday could be trusted to work tomorrow. That world, the world of savanna and forest and coastline of fire and shelter and tool, was governed by rules that feel self-evident because they were self-evident to survival. And so the brain that emerged from that history is a brain exquisitely tuned to those rules. It is a brain that finds Newtonian physics intuitive, not because Newtonian physics is simple, but because Newtonian physics approximately describes the conditions under which human cognition evolved. Spacetime does not operate under those conditions. It operates at speeds our bodies will never reach near masses, our environments never contained across distances that have no analog in any landscape a human being has ever walked through. The rules of spacetime are not counterintuitive in the way that a difficult puzzle is counterintuitive, the kind of counterintuitive that resolves with enough thought. They are counterintuitive in a deeper sense. They describe a reality that the architecture of human perception was never designed to represent. No amount of thinking will make time dilation feel natural the way falling feels natural. No mental effort will make length contraction feel as obvious as the fact that a closer object looks larger. These things remain permanently strange, not because we are not trying hard enough, but because the cognitive tools we are trying with were built for an entirely different job. This distinction matters, because when people encounter space-time and find it difficult, they often conclude that they are simply not smart enough, or that physics is too abstract, or that the subject requires a level of mathematical sophistication they do not possess. None of those things are true. The difficulty is not personal, it is structural, and recognizing that changes the nature of the effort. Instead of trying to make space-time feel intuitive, which is a battle you will lose, the goal becomes something different. It becomes learning to hold the idea at arm's length, to understand it, without demanding that it feel familiar, to let it exist in the mind as something genuinely strange, rather than forcing it into a shape it does not have. With that in mind, consider what Einstein was actually doing in 1905. He was not trying to overturn Newtonian physics. He was not trying to be radical. He was in fact trying to be conservative, trying to preserve something that he considered essential. That something was the principle of relativity, which stated simply that the laws of physics should be the same for all observers moving at constant velocities relative to one another. This seemed obviously correct. If you are on a smoothly moving train with no windows, there is no experiment you can perform inside that train that will tell you whether you are moving or standing still. The laws of physics do not favor one inertial reference frame over another. They are the same everywhere. The problem was that Maxwell's equations appeared to violate this principle. They predicted a specific fixed speed for light. If the laws of physics, including Maxwell's equations, were the same for all observers, then every observer should measure the same speed of light, regardless of their own motion. But that contradicted everything Newtonian mechanics said about relative velocities. If you are moving toward a light source at half the speed of light, Newtonian logic says you should measure the light approaching you at 1.5 times its normal speed. Maxwell's equations said you would still measure exactly the same speed as someone standing still. These two things could not both be right. Something had to give. Most physicists of the era assumed Maxwell's equations were the problem. They assumed that a more complete theory would eventually fix the inconsistency and restore the familiar Newtonian picture of velocities adding and subtracting cleanly. Einstein made the opposite assumption. He decided to take Maxwell's equations seriously, to assume that the speed of light really was constant for all observers, and to ask what else would have to be true for that to be the case. The answer he arrived at was the one that changed everything. If the speed of light is fixed, then the things we assumed were fixed. Distances and durations are not. Time and space must adjust themselves for every observer in such a way that the speed of light remains constant for all of them, and if space and time adjust, then they cannot be independent. They must be woven together. They must be a single fabric, a single structure that responds to motion. This is the moment the concept of space-time was born. Not from a laboratory discovery, not from a dramatic experimental result, from a thought experiment, from a young man in a patent office deciding to take an equation seriously and following the logic wherever it led, no matter how strange the destination. There is something almost unbearably human about that image, the most fundamental restructuring of our understanding of physical reality, emerging not from expensive equipment or institutional power, but from concentrated thought and the willingness to be wrong about everything comfortable. The initial theory Einstein published in 1905 dealt with objects moving at constant velocities relative to one another. It is called special relativity. It established that time slows down with increasing speed, an effect called time dilation. It established that lengths contract in the direction of motion, an effect called length contraction. It established the equivalence of mass and energy, summarized in what became the most famous equation in human history. And it established that simultaneity, the question of whether two events happen at the same moment, is not absolute. Two observers moving relative to each other can genuinely irreconcilably disagree about whether two distant events happened at the same time. Not because one of them is wrong, because the concept of simultaneity is not a fixed property of the universe. It is a property of a reference frame. Sit with that for a moment. There is no universal now. There is no cosmic clock that everyone shares. What counts as the present moment depends on how fast you are moving and in what direction. Two people passing each other on the street moving at slightly different velocities inhabit very slightly different versions of now. The difference at everyday speeds is so minuscule as to be practically non-existent. But it is real. It is measurable with precise enough instruments. And at speeds approaching the speed of light, the disagreements about simultaneity become enormous. This is not a philosophical position. It is a physical fact confirmed by experiment after experiment for more than a century. And yet, even knowing all of this, even accepting it intellectually, even understanding the mathematics, it still does not feel real. That is the point. That is precisely the thing to hold on to. The inability to feel it is not an obstacle to understanding it. It is simply a feature of the landscape. Space-time is genuinely alien to human intuition, and the correct response to that alienness is not to paper over it with inadequate metaphors, but to acknowledge it directly. The rubber sheet analogy, the one with the bowling ball curving the fabric and smaller balls rolling in spirals around it, is useful as a first gesture. It conveys something true about how mass influences the paths of nearby objects, but it is misleading in almost every other respect. The sheet curves downward because of actual gravity pulling on it in a world outside the analogy. The real curvature of space-time is not a dip into some larger space. Space-time is not inside anything. It is the thing that everything else is inside of. When it curves within itself, into no external direction, against no external backdrop. That kind of curvature has no image in ordinary experience, because ordinary experience never required one. What Einstein showed in his second theory, the general theory of relativity, published in 1915, was that gravity itself is not a force in the Newtonian sense. It is the curvature of space-time caused by mass and energy. When the Earth orbits the Sun, it is not being pulled by a force radiating outward from the Sun across empty space. It is following the straightest possible path through a space-time that has been curved by the Sun's enormous mass. That path, which appears curved from our perspective, is actually the most direct route available through the geometry. Objects in freefall, astronauts in orbit, planets circling stars, light bending around galaxies, are not being pushed or pulled. They are simply moving along the natural contours of the space-time landscape surrounding them. This reframing of gravity from a force to a geometry was not just a different way of describing the same thing. It made new predictions that Newtonian gravity could not make. It predicted that light, despite having no mass, would bend around massive objects because it travels through space-time and space-time curves. In 1919, Arthur Eddington observed a solar eclipse and measured the positions of stars near the edge of the Sun. Their apparent positions were shifted slightly from where they should have been shifted by exactly the amount Einstein's equations predicted. It was one of the most dramatic confirmations in the history of science. A German physicist's theory confirmed by a British expedition in the immediate aftermath of the First World War. The event made Einstein a global celebrity overnight. But here is what that triumph did not resolve. Here is what the equations precise and confirmed as they were left completely open. They described how spacetime curves. They described what curvature does to the paths of objects and light. They described the relationship between mass, energy, and geometry with a precision that has never been exceeded. What they did not describe, what they could not describe, was the underlying nature of the thing that was curving, spacetime. In Einstein's theory is the stage. It is the arena. It is the medium through which everything moves. But the theory says almost nothing about what the stage itself is made of, or whether it is made of anything at all, or whether the concept of being made of something even applies to it. These questions were not oversights. They were not details left for later. They pointed towards something that could not be reached by the tools Einstein had built. And there was another problem waiting just around the corner. A problem that had nothing to do with the large-scale behavior of stars and galaxies. A problem that lived at the opposite extreme in the smallest, densest, most violent regions of the universe. A problem that had been quietly growing in the background while relativity was reshaping the cosmos. The problem of what happens when spacetime curves so severely that our equations collapse. The problem of what happens when the two greatest theories in physics look each other in the eye and realize, with a kind of terrible clarity, that they are speaking entirely different languages. That is what comes next. 0905. Claude responded, "There is a moment in the history of science that deserves to be experienced slowly. There is a moment in the history of science that deserves to be experienced slowly, not rushed past in a summary, not reduced to a footnote in a larger story, but held open long enough to feel the full weight of what changed. It is the moment when a human being first understood, with genuine mathematical precision, that the universe does not operate on a fixed stage, that the arena itself is a participant. That space is not the absence of something, but the presence of something. Something active, something responsive, something that bends and shifts and carries within its geometry the entire history of everything that has ever moved through it. To reach that moment, you have to go back further than Einstein. You have to go back to a problem that had been bothering astronomers for decades before Einstein was born. The planet Mercury, the smallest and innermost planet in our solar system, does something that no planet in the Newtonian picture was supposed to do. Its orbit around the Sun is not a perfect fixed ellipse. It precesses. The point at which Mercury comes closest to the Sun shifts slowly over time, tracing a rosette pattern across the sky rather than repeating the same closed loop indefinitely. Most of this precession could be explained by the gravitational influences of the other planets, but not all of it. There was a small residual, a discrepancy of roughly 43 arc-seconds per century, that Newtonian gravity simply could not account for. 43 arc-seconds per century. To put that in perspective, imagine dividing a full circle into 1,296,000 equal parts. The unexplained drift of Mercury's orbit amounted to 43 of those parts every 100 years. It was an almost incomprehensibly tiny anomaly, and yet it refused to go away no matter how carefully astronomers refined their calculations. For decades, the leading explanation was the existence of an undiscovered planet orbiting even closer to the Sun than Mercury, whose gravitational pull would account for the discrepancy. Astronomers even gave it a name, Vulcan. They searched for it during solar eclipses. They never found it, because it did not exist. The discrepancy was not caused by a missing planet. It was caused by the fact that Newtonian gravity was not quite right. When Einstein completed his general theory of relativity in November 1915 and applied it to the orbit of Mercury, the 43 arc-seconds fell out of the equations exactly. Not approximately, not roughly, exactly. Einstein later said this discovery gave him heart palpitations. After years of struggle, after false starts and mathematical detours and moments of deep uncertainty, here was the universe confirming that the geometry he had been building was real, that the curvature of space-time was not just a beautiful abstraction, it was the actual mechanism by which the solar system operated. But the confirmation that reached the wider world came 4 years later in May of 1919 during a total solar eclipse visible from the island of Principe off the west coast of Africa and from Sobral in northern Brazil. Arthur Eddington, a British astrophysicist who had been one of the few people to fully grasp Einstein's theory during the war years, led the expedition to Principe. The goal was to measure the positions of stars near the edge of the sun during the brief minutes of totality, when the moon blocked the sun's light enough to make those stars visible. Einstein's theory predicted that the sun's mass would curve the surrounding spacetime, and that light from distant stars passing close to the sun would follow that curvature, arriving at Earth from a slightly different direction than it would if the sun were not there. The stars' apparent positions would be shifted by a specific calculable amount. When Eddington compared the photographic plates taken during the eclipse to reference plates taken months earlier, the shift was there, precise, matching the prediction. The geometry of space-time bent by the mass of the sun had redirected the light of stars. Not through any force, not through any push or pull, through pure curvature. The announcement made front pages around the world. The Times of London declared that the fabric of the universe had been rewoven. Einstein became almost overnight the most famous scientist alive. But what most of those newspaper readers did not fully grasp, and what is still easy to miss even now, is what the confirmation actually meant. It was not simply that a new theory had replaced an old one. It was that the entire conceptual framework through which humanity understood space had shifted. Space was no longer empty. Space was no longer passive. Space was a geometric structure that participated actively in the behavior of everything within it. And time was not a separate river flowing parallel to events. It was threaded through the same structure, bending with it, slowing near masses, speeding away from them. The universe did not happen inside space and time. The universe happened as space and time. To feel the true strangeness of this, consider what it means for something as familiar as falling. When you drop an object and watch it accelerate toward the ground, every intuition you have tells you that something is pulling it downward, a force, an attraction between masses. This is Newton's picture, and it is not wrong exactly. It is an extraordinarily accurate approximation for the conditions of everyday life. But it is not the complete picture. In Einstein's framework, when you drop an object and release it, you are not watching it being pulled. You are watching it follow the most natural path available to it through the curved spacetime surrounding Earth. Spacetime near Earth curves inward toward Earth's center. An object released from your hand simply follows that curvature. It is in a precise geometric sense moving in a straight line, the straightest line available in a curved space. The path curves toward Earth because space-time curves toward Earth. The object is not falling. It is coasting. What you feel when you stand on the ground is not the force of gravity pulling you down. It is the ground pushing you up. The ground is preventing you from following your natural path through curved space-time, which would take you toward Earth's center. The sensation of weight is not gravity. It is resistance to gravity. It is the floor refusing to let you move the way space-time is trying to guide you. This inversion, the realization that standing still is the active state and free fall is the passive one, is one of the most disorienting conceptual shifts in all of physics. And it remains disorienting no matter how many times you encounter it, because nothing in ordinary experience prepares you for it. Now, take this further. If massive objects curve the spacetime around them, and if the curvature grows more intense as mass increases or distance decreases, then there must be a limit somewhere. A point at which the curvature becomes so extreme that the geometry of spacetime itself begins to break. Consider what happens as you compress mass into a smaller and smaller volume. The curvature around it deepens. The paths available to nearby objects bend more and more severely. Light, which follows the curvature of spacetime, just as matter does, must travel along increasingly distorted routes. At a certain threshold, a boundary called the event horizon, the curvature becomes so steep that no path leads outward anymore. Every available trajectory for matter and light alike curves back inward. Nothing escapes. Not because something grabs it and holds it, but because the geometry has closed in on itself. All roads lead inward. There are no roads leading out. This is a black hole. And it is not a place where the laws of physics are suspended. It is a place where the laws of physics, specifically the law that space-time curves in response to mass and energy, are followed to their ultimate conclusion. The event horizon is not a physical surface. It is a geometric boundary, a region where the curvature has reached a point of no return. Cross it and the structure of space-time ensures there is no path back to the outside universe. Time itself, near the event horizon, behaves in ways that strain every intuition. An observer falling toward a black hole would experience nothing unusual as they cross the horizon. No wall, no barrier, no moment of special drama. They would simply find themselves inside a region from which no signal could reach the outside. But to an observer watching from far away, something deeply strange would appear to happen. As the falling observer approached the horizon, they would appear to slow down. Their signals would become increasingly redshifted, their motion increasingly frozen. They would never appear to cross. They would seem to hover at the threshold forever, dimming and reddening, trapped at the boundary for all time. Both perspectives are correct. Both are real descriptions of what is happening in the curved space-time near a black hole. The disagreement between them is not an illusion, it is the geometry. Inside the event horizon, according to Einstein's equations, space-time curves toward a point called a singularity. At the singularity, the curvature becomes infinite. Density becomes infinite. The equations produce results that are not just large, they are meaningless. Physically, mathematically, conceptually meaningless. And this is where the extraordinary precision of general relativity encounters its limit. Not its experimental limit, its conceptual limit. The theory that described Mercury's orbit with perfect accuracy, that bent the light of stars exactly as predicted, that has been confirmed in experiment after experiment for a century. This same theory, when pushed to the center of a black hole, simply stops working. It does not produce wrong answers. It produces no answers at all. This breakdown is important. It is not a technical problem waiting for a better computer. It is a signal that at the extreme end of what general relativity describes, something else must take over. Some other framework must apply. Some deeper theory must exist that contains general relativity as a special case, accurate under ordinary conditions but superseded when those conditions become extreme enough. That deeper theory does not yet exist in complete form, which means that at the center of every black hole in the universe, at those points where the geometry of space-time curves past all limits, there is a region of reality that no human theory can currently describe. Not approximately, not roughly, not at all. And the problem is not isolated to black holes. It appears at the other extreme of scale as well. When you trace the expansion of the universe backward in time, following the geometry as it contracts and heats and densifies, you eventually reach conditions that resemble those inside a black hole. You reach a moment when everything we can observe was compressed into a region smaller than an atom. A moment when temperatures were so extreme and densities so unimaginable that general relativity and quantum mechanics, the two pillars of modern physics, both needed to apply simultaneously. And in that moment they contradict each other. They produce incompatible descriptions of the same reality. A reality that clearly existed because we are the result of it. This is the wall. This is where the story of space-time stops being a story of triumph and becomes a story of something more honest, of two extraordinarily successful theories staring at each other across a chasm neither can bridge. You now understand the shape of space-time well enough to feel the edges of that chasm. You have seen how it bends around mass, how it guides the paths of planets and light, how it slows time near massive objects and closes in on itself inside black holes. You have seen the predictions confirmed. The experiments validated, the equations tested to precision, and you have seen where all of that precision suddenly completely runs out. What lies beyond that edge? What theory might one day fill the silence at the center of a black hole and at the birth of the universe is where the deepest questions begin. And to understand why those questions are so hard, you need to understand something about the other framework. The one that lives at the opposite extreme, the one that governs the world of the unimaginably small, the one that is, in almost every important respect, the most successful scientific theory ever constructed, and the one that, when placed next to general relativity, produces a collision from which neither emerges unscathed. The next chapter begins there, in the world beneath the atom, where certainty dissolves, where particles refuse to have definite locations, where the very act of observation changes the thing being observed, where the rules are so different from anything in ordinary experience that even the physicists who built the theory spent decades arguing about what it meant, where spacetime itself, the smooth curved geometry that Einstein gave us, begins to crack. There is a number that should stop you completely. Not because it is large in the way that astronomical distances are large. You have grown somewhat accustomed to large numbers by now, to light years and billions of years and masses measured in solar units. This number is different. This number represents not a distance or a duration, but a failure. A precise, quantifiable, experimentally confirmed failure at the very heart of our understanding of physical reality. The number is 10 to the power of 120. Written out, it is a 1 followed by 120 zeros. It is by any reasonable measure the largest discrepancy between a theoretical prediction and an experimental observation in the entire history of science. And it sits directly at the intersection of the two theories that together are supposed to explain everything. To understand where this number comes from, you need to understand something about empty space. Not the poetic idea of emptiness, the vast darkness between stars, the silence of the void. The physical reality of what happens in a region of space when you remove every particle, every photon, every detectable form of matter and energy. What remains? In the picture provided by classical physics, the answer is simple. Nothing. A true vacuum is the complete absence of everything. A perfectly neutral backdrop. A stage with no actors and no scenery. But quantum mechanics, which governs the behavior of nature at the smallest scales, does not permit this kind of emptiness. Quantum mechanics insists that a true vacuum, a region of space with precisely zero energy, is impossible. The reason comes from one of the most fundamental principles of the theory, the Heisenberg uncertainty principle, which states that certain pairs of physical quantities cannot both be precisely defined at the same moment. Energy and time form one such pair. If a region of space had exactly zero energy at exactly every moment, both quantities would be precisely defined simultaneously. Quantum mechanics forbids this, and so even empty space must fluctuate. It must contain random temporary bursts of energy, appearing and disappearing continuously, too brief to observe directly, but real in every measurable sense. These are called vacuum fluctuations, and they have observable consequences. They cause tiny shifts in the energy levels of atoms that have been measured with extraordinary precision. They produce a measurable force between two uncharged metal plates, placed very close together, a phenomenon called the Casimir effect, confirmed experimentally many times over. The fluctuations are real. The vacuum is not empty. Now, here is where the catastrophe begins. If the vacuum contains energy, if empty space is not truly empty but seething with quantum activity, then that energy has a value. Physicists can calculate what that value should be using the equations of quantum field theory, the framework that extends quantum mechanics to describe fields and particles. When they perform this calculation, the result is staggering. The predicted energy density of the vacuum is approximately 10 to the power of 120 times larger than what we actually observe. 10 followed by 120 zeros. The universe we live in has a vacuum energy. We can measure it indirectly through the accelerating expansion of the cosmos. That measured value is real and finite and small. The value predicted by our best theory of the quantum world is larger by a factor that exceeds the total number of atoms in the observable universe by an almost incomprehensible margin. If the quantum prediction were accurate, if empty space actually contained as much energy as the equations suggest, the curvature of spacetime would be so extreme that the universe would either have collapsed back on itself in an instant or expanded so violently that no structure of any kind, no atoms, no stars, no galaxies, no anything could ever have formed. The universe would be unrecognizable. It would not exist in any form we could inhabit or observe, and yet here we are. The universe exists. It is expanding at a measured rate. Galaxies form, stars burn. You are here encountering this number, which means the number must be wrong, or the theory must be incomplete, or something is cancelling out the enormous quantum prediction to leave behind the tiny observed value, some mechanism, some symmetry, some deeper principle that we have not identified. This is not a small adjustment waiting to be made. This is not a rounding error or a missing constant. This is the largest quantitative failure in the history of theoretical physics, sitting in plain sight at the boundary between quantum mechanics and general relativity, unresolved after decades of effort by some of the most brilliant people who have ever lived. And it is only the most dramatic example of a much broader problem. The problem is this: general relativity and quantum mechanics are individually the two most successful scientific theories ever constructed. General relativity describes the behavior of gravity spacetime and the large-scale structure of the universe. It has been tested in conditions ranging from the orbit of Mercury to the merging of black holes a billion light-years away. Every prediction it has ever made has been confirmed. Quantum mechanics extended into quantum field theory describes the behavior of particles, fields, and forces at the smallest accessible scales. It predicted the existence of antimatter before it was discovered. It predicted the Higgs boson decades before the Large Hadron Collider confirmed it. Its predictions have been verified to a precision of 1 part in 10 billion, the equivalent of measuring the distance from New York to Los Angeles to within the width of a human hair. These are not approximate theories. They are not frameworks waiting to be refined. They are within their respective domains, essentially exact descriptions of physical reality, and they cannot be combined. This is the central crisis. This is the thing that makes every physicist who works at the frontier of fundamental physics acutely uncomfortable. When you try to apply the mathematical tools of quantum mechanics to the geometry of spacetime, when you try to quantize gravity the way you quantize electromagnetism or the strong nuclear force the equations explode, they produce infinities that cannot be removed or absorbed, the way similar infinities in other quantum theories can be tamed through a process called renormalization. The mathematics becomes not merely difficult but genuinely incoherent. It produces predictions of infinite probability, infinite energy, quantities that are not just wrong but meaningless. A theory that produces infinities at every step is not a theory. It is a sign that something in the foundations is broken. This is the wall that physicists have been running into for nearly a century, and to understand why it is so hard, you need to understand the nature of the incompatibility. It is not simply that one theory is more complicated than the other, or that the mathematics of one is unfamiliar to practitioners of the other. The incompatibility is structural. It goes all the way down to the basic assumptions each theory makes about the nature of reality. General relativity assumes that spacetime is smooth and continuous, that you can always zoom in further and find a perfectly well-defined geometry, a precise curvature, a precise distance, a precise passage of time. The theory is built on the mathematics of smooth manifolds, on the assumption that space and time form a fabric without gaps or granularity. Quantum mechanics assumes the opposite. It assumes that nature is fundamentally granular, that energy comes in discrete packets, that measurements have inherent uncertainties that cannot be eliminated, that the act of observing a system inevitably disturbs it, that nothing, not position, not momentum, not energy, can be simultaneously and perfectly defined. These two sets of assumptions cannot both be literally true at every scale. Something must give. And the place where the giving happens, the place where the smooth geometry of relativity meets the grainy uncertainty of quantum mechanics, is precisely where our understanding runs out. Consider what happens when you try to examine spacetime at the smallest possible scales. In general relativity, you can zoom in as far as you like, and the geometry remains well-defined. But quantum mechanics says that probing smaller distances requires larger energies, a consequence of the uncertainty principle. The smaller the region you want to examine, the more energy you must concentrate into it. At a scale called the Planck length, approximately 10 to the minus 35 meters, a distance so small that a proton is larger by roughly the same factor that a proton is larger than the observable universe, the energy required to probe that scale becomes so large that the spacetime geometry in that region becomes violently unstable. The act of looking at spacetime at those scales would create gravitational distortions so extreme that the measurement would destroy itself. The geometry would fluctuate wildly unpredictably in ways that the smooth mathematics of general relativity cannot describe, and the quantum framework has no language for. At the Planck scale, Spacetime as we know it ceases to be a useful concept. Something else must take over. We do not know what. This is not an obstacle in the sense of a problem waiting for a clever solution. It is a signal. It is the universe telling us, with considerable mathematical force, that the picture we have, the picture of a smooth curved spacetime on one hand and a granular quantum world on the other, is not the complete picture. Somewhere beneath both descriptions is a deeper reality that gives rise to both. A reality in which the apparent conflict between smooth geometry and quantum uncertainty is resolved because both emerge as approximate descriptions of something more fundamental, something we have not yet found. But the incompatibility goes deeper still. It is not only about scales and distances, it is about the nature of time itself. In general relativity, time is a dimension, a genuine geometric component of space-time woven into the fabric alongside the three spatial dimensions. Time is flexible. It stretches near massive objects. It contracts with increasing velocity. It is not a parameter that runs independently in the background. It is part of the structure being described. In quantum mechanics, time plays an entirely different role. It is a fixed external parameter, an independent variable against which the evolution of quantum systems is measured. It does not stretch or curve. It does not respond to mass or motion. It ticks forward at a uniform rate as the backdrop against which quantum states evolve. These two descriptions of time, one flexible and geometric, the other fixed and external, cannot both be correct at a fundamental level. They describe time in ways that are not merely different, but mutually exclusive. And since any unified theory would need to describe time consistently, this mismatch is not a technical detail. It is a foundational problem that cuts to the heart of what physical reality actually is. There is a third incompatibility that deserves its own moment of attention. In quantum mechanics, information is conserved. This is not an optional feature of the theory. It is built into the mathematical structure at the deepest level. The evolution of a quantum system is described by an equation, the Schrödinger equation, that is perfectly reversible. If you know the complete quantum state of a system at any moment, you can in principle calculate its state at any other moment, past or future. No information is ever created or destroyed. It may become scrambled beyond practical recovery, but it is always there in principle encoded somewhere in the quantum state of the universe. General relativity, however, appears to violate this principle. When matter falls into a black hole, the information about its quantum state, the details of every particle that ever constituted it, appears to be irretrievably lost. The black hole eventually evaporates through the process of Hawking radiation, a quantum effect discovered theoretically by Stephen Hawking in 1974, but the radiation appears to carry no information about what fell in. It is thermal, random. It describes the temperature of the black hole, but not the history of what created it. If the information is truly gone, quantum mechanics is violated. If the information is somehow preserved, then either our understanding of black holes or our understanding of quantum mechanics or both must be wrong in ways we have not yet identified. This is the black hole information paradox. It is not a paradox in the colloquial sense of a clever puzzle with a hidden solution. It is a genuine unresolved conflict between two theories that are each individually confirmed to extraordinary precision, producing incompatible predictions about the same physical situation. For decades, the majority of physicists assumed the information must somehow be preserved, that Hawking's calculation, while brilliant, must be missing something. But identifying what it is missing has proven extraordinarily difficult. The paradox remains open, and its openness is a symptom of the deeper problem. Two theories that work perfectly in their own domains, reaching their boundary conditions and finding that the boundary itself is a contradiction. What this means, what all of this means, is that our current picture of reality has a seam running through it, a visible join between two frameworks that were built independently, tested independently, and confirmed independently, but never successfully unified. On one side of the seam, the smooth curved geometry of spacetime. On the other side, the granular, uncertain world of quantum fields. The seam runs through black holes. It runs through the first moments of the universe. It runs through the vacuum energy catastrophe. It runs through the incompatible treatments of time. It is not hidden, It is not subtle. It is the most obvious structural feature of fundamental physics, sitting in plain sight, defying every attempt to close it. And yet something important follows from this. The seam is not evidence of failure, it is evidence of progress. A century ago, we did not know where the edges of our theories were. We did not know what questions to ask at the boundary. The fact that we can now describe the incompatibility precisely, that we can point to the specific places where the two frameworks collide and identify the exact nature of the contradiction, means that we have gotten close enough to see the shape of what we do not know. That is not nothing. That is in many ways everything, because the shape of what you do not know is the map that guides you toward what comes next. What comes next involves looking even more carefully at those places where the seam is most visible, at the pieces of the puzzle that refuse to fit into either framework, at the anomalies and paradoxes and missing explanations that accumulate around the boundary between the known and the unknown, because in those accumulations scattered across the landscape of unsolved problems there are clues, faint ones, incomplete ones, but clues nonetheless, and they all point in the same direction, towards something deeper than space-time itself. 0939, Claude responded. There is a particular kind of map that explorers sometimes carried in the age before satellites and aerial surveys. There is a particular kind of map that explorers sometimes carried in the age before satellites and aerial surveys. A map where the known coastlines were drawn with careful precision, every inlet, every headland, every depth sounding recorded faithfully from direct observation, and then at the edges of the known world, the precision would dissolve. The coastline would become approximate, then speculative, then absent, entirely replaced by blank parchment, or in some cases, the cartographer's honest admission here there be dragons. Not because dragons existed, but because the honest thing to say about a region you have never visited and cannot describe is that you do not know what lives there. The unknown deserves to be marked as unknown. What physics has accumulated over the past century is something like that map. In the center, where conditions are moderate and instruments are adequate, the picture is extraordinarily precise. But at the edges, at the extreme scales, the extreme densities, the extreme distances, the precision softens and the blank parchment begins. And scattered across that parchment in the regions where certainty gives way to inference, there are markings, not dragons, something stranger. A collection of unsolved puzzles, unexplained observations, and persistent anomalies that do not fit neatly into either of the two great frameworks. Each one taken alone might seem like a detail. Taken together, they outline something, the shape of a much larger question. Begin with the rotation of galaxies. In the 1970s, an astronomer named Vera Rubin, working with her colleague Kent Ford, undertook a systematic study of how stars move within spiral galaxies. The expectation based on Newtonian gravity, and confirmed by the behavior of our own solar system, was straightforward. Stars farther from the galactic center, where most of the visible mass is concentrated, should orbit more slowly, just as the outer planets of our solar system orbit more slowly than the inner ones. Neptune moves far more slowly in its orbit than Mercury. The same relationship should hold for stars in a galaxy. What Rubin and Ford found was that it did not. Stars at the outer edges of galaxies were moving at roughly the same speed as stars much closer to the center. In some cases, the rotation curve, the graph of orbital speed against distance from the center, was essentially flat, not declining, flat. This was not a small discrepancy, easily attributed to measurement error. It was a systematic repeating pattern observed across dozens of galaxies. The stars were moving too fast, far too fast. They should by all rights be flying off into intergalactic space. The visible mass of the galaxy could not possibly generate enough gravitational pull to hold them in their orbits at those speeds. The conclusion was uncomfortable but unavoidable. There must be more mass than what we can see. Invisible mass. Mass that does not emit light, does not absorb light, does not interact with electromagnetic radiation in any way we can detect. Mass that nevertheless has gravitational influence, that curves space-time, that holds galaxies together, that shapes the large-scale structure of the universe. This hypothetical substance was given a name, dark matter, and in the decades since Rubin's observations, the evidence for its existence has only grown. The bending of light around galaxy clusters, a phenomenon called gravitational lensing, a direct consequence of general relativity, reveals mass distributions that extend far beyond the visible stars and gas. The patterns of the cosmic microwave background, the faint afterglow of the early universe, require the presence of dark matter to explain the specific distribution of temperature variations across the sky. Simulations of cosmic structure formation only produce results that match observations when dark matter is included. The evidence is overwhelming. Dark matter is real. It constitutes approximately 27% of the total energy content of the universe. And we have absolutely no idea what it is. Not approximately no idea. Not a vague idea waiting to be sharpened. No idea. Every candidate particle predicted by extensions of the standard model of particle physics, every hypothetical weakly interacting particle that might plausibly constitute dark matter, has been searched for and not found. Experiments buried deep underground, shielded from cosmic radiation, designed with extraordinary sensitivity to detect the faint recoil of a dark matter particle colliding with an ordinary atomic nucleus, have returned null results year after year. Particle accelerators at the highest energies ever achieved have found no hint of the particles that leading theories predicted. Whatever dark matter is, it is not any of the things we expected it to be. It interacts gravitationally, it shapes spacetime. Beyond that, it remains hidden, a substance that constitutes more than a quarter of everything, utterly invisible and utterly unidentified. Dark energy is stranger still. In 1998, two independent teams of astronomers, the Supernova Cosmology Project and the High-Z Supernova Search Team, were studying a particular class of stellar explosion called a Type Ia supernova. These explosions are useful to cosmologists because they always release approximately the same total amount of energy, making them what astronomers call standard candles objects, whose intrinsic brightness is known so that their apparent brightness in the sky reveals their distance. By measuring the distances to Type Ia supernovae in distant galaxies and comparing them to how fast those galaxies are receding, the teams expected to measure the rate at which the universe's expansion was slowing down. Gravity pulls matter together. The expansion of the universe set in motion by the Big Bang should be decelerating under the mutual gravitational attraction of all the matter and energy within it. The question was simply how fast the deceleration was occurring. What both teams found independently and simultaneously was that the expansion was not decelerating. It was accelerating. The universe was not slowing its expansion under gravity's influence. It was expanding faster and faster over time. Something was pushing it apart. Something with a repulsive effect spread uniformly through all of space, growing stronger as the universe grew larger. Something that behaved, in the equations of general relativity, like energy built into the vacuum itself, built into the geometry of empty spacetime. It was given the name dark energy, and it constitutes approximately 68% of the total energy content of the universe, the largest single component of everything that exists, and we have again absolutely no idea what it is. Notice what this means. The ordinary matter atoms, molecules, stars, planets, gas, clouds, everything that has ever been directly detected or observed constitutes approximately 5% of the universe. The remaining 95% consists of dark matter and dark energy, neither of which fits into the standard model of particle physics, neither of which has been directly detected, and neither of which is explained by either of our two great theoretical frameworks. We have built the most precise and successful theories in the history of science. We have tested them with instruments of extraordinary sophistication, and those theories together describe 5% of what exists. The universe, in an almost literal sense, is 95% unknown. This would be humbling enough on its own, but the puzzle does not stop there. Return to black holes, and to the question of what happens to the information contained in matter that falls past the event horizon. Stephen Hawking's 1974 discovery that black holes emit radiation, now called Hawking radiation, was one of the most remarkable theoretical results of the 20th century. It arose from applying quantum field theory to the space-time geometry near a black hole's event horizon. In the quantum vacuum, Virtual particle pairs constantly appear and disappear. Near the event horizon, occasionally one particle of such a pair falls inward while the other escapes outward. The escaping particle carries energy away from the black hole. Over time, over an almost incomprehensibly long time for a stellar mass black hole, this process causes the black hole to lose mass and eventually evaporate entirely. The radiation carries away the black hole's energy. But according to Hawking's calculation, the radiation is perfectly thermal. It carries no information about the specific quantum states of the matter that originally formed the black hole or subsequently fell into it. If the black hole evaporates completely, that information appears to be gone permanently, which, as we established, quantum mechanics says is impossible. This is more than an abstract puzzle. It is a direct conflict between two confirmed theories about the fate of something as concrete and physical as the information content of matter. Hawking himself initially argued that the information was genuinely lost, that black holes represented a fundamental breakdown of quantum mechanical unitarity. Most physicists disagreed, but for decades no one could say precisely how the information was preserved. Recent work, including calculations involving what is called the island formula, and contributions from the entanglement structure of the radiation, suggests that the information may after all be encoded in subtle quantum correlations in the Hawking to radiation, but the mechanism remains incompletely understood, and the calculations required to demonstrate this fully push beyond the limits of current mathematical tools. The paradox is not resolved. It is partially illuminated. There is a difference. Then there is the arrow of time. This is perhaps the most quietly unsettling puzzle in all of physics because it touches something we experience every single moment of our lives, and yet cannot explain. Time has a direction. The past is fixed and the future is open. You can remember yesterday but not tomorrow. You can stir cream into coffee but you cannot unstir it. Broken glasses do not spontaneously reassemble. These asymmetries are so fundamental to experience that it is almost impossible to imagine their absence. And yet, and this is the disturbing part, the fundamental equations of physics are almost entirely symmetric in time. Run them forward and they describe the evolution of a system. Run them backward and they describe an equally valid evolution. Newton's laws are time-symmetric. Einstein's equations are time-symmetric. The Schrödinger equation of quantum mechanics is time-symmetric. Even the equations governing particle interactions at the deepest level are, with one tiny exception, in a rare class of particle decay, time-symmetric. The laws of physics do not prefer a direction of time. They work equally well in both directions, and yet time in every observable phenomenon at the macroscopic scale flows unmistakably in one direction only. The explanation most commonly offered, that the arrow of time arises from the second law of thermodynamics, from the tendency of systems to evolve towards states of higher entropy, is correct as far as it goes. But it does not explain why the universe began in such an extraordinarily low entropy state in the first place. It does not explain why the initial conditions of the Big Bang were arranged so precisely that entropy had an enormous distance left to increase, giving time its direction for the billions of years since. The arrow of time is not explained by our theories. It is described by them, and its origin remains genuinely mysterious. There is also the fine-tuning problem. The constants of nature, the strength of gravity, the mass of the electron, the charge of the proton, the cosmological constant associated with dark energy take values that appear to a remarkable degree to be precisely calibrated for the existence of complex structures. Change the strength of the strong nuclear force by a few percent and carbon, the backbone of chemistry, as we know it, cannot form in stellar interiors. Change the cosmological constant by even a tiny fraction, and the universe either collapses before galaxies can form or expands so rapidly that matter never has time to clump into anything. Change the mass of the electron and chemistry as we know it becomes impossible. The constants seem fine-tuned. Not in a supernatural sense, there is no scientific evidence for intentional design, but in the sense that the values these constants take are deeply puzzling. Our theories describe them. They do not explain them. We have no idea why the constants have the values they do. We cannot derive them from deeper principles. They are inputs to our theories, not outputs. And their apparent fine-tuning for complexity is one of the most discussed and least resolved puzzles in fundamental physics. There is also the matter of quantum entanglement, which grows stranger the more carefully you examine it. When two particles interact and then separate, they can remain in what is called an entangled state, a state in which the quantum properties of one particle are correlated with the quantum properties of the other, regardless of how far apart they have traveled. Measure one particle, and the other instantly reflects a correlated result, not after a delay proportional to the distance. Instantly. This was confirmed experimentally by John Bell's theorem, and subsequent experiments most definitively by Alan Aspect's 1982 experiments, and more recently by loophole-free Bell tests in 2015. Entanglement is real. The correlations it creates cannot be explained by any hidden classical mechanism. They are genuine quantum correlations that appear to transcend spatial separation, and yet no information is transmitted faster than light. No signal passes between the particles. The correlations are there, but they cannot be exploited to send a message. They are a feature of quantum reality that sits in deep tension with the space-time picture of general relativity, a picture in which locality, the principle that what happens here cannot instantly affect what happens there, is fundamental. Entanglement does not violate locality in the strict sense, but it strains the picture. It suggests that the quantum description of reality operates through connections that space-time as we understand it does not adequately accommodate. All of these puzzles, dark matter, dark energy, the black hole information, paradox, the arrow of time, fine-tuning, quantum entanglement, share a common feature. They are not failures of experiment. Our instruments have not let us down. They are failures of explanation. We can observe these phenomena. We can describe them mathematically to varying degrees of precision. What we cannot do is place them within a coherent, unified picture of what physical reality fundamentally is. They are the places where the map runs out, where the known coastline gives way to blank parchment. And taken together, they are telling us something. Not in the dramatic language of crisis. Physics is not in crisis in the sense of imminent collapse. It is in crisis in the sense of standing at a genuine boundary looking out at territory it has not yet found the tools to enter. But here is what is remarkable about that boundary of flocklie. Each one points in a direction, and when you follow those directions, when you trace the lines along which the puzzles are arranged and ask what structure they might all be edges of, you begin to arrive at a possibility so strange, so counterintuitive, and yet so consistent with everything the puzzles are suggesting that it deserves its own careful consideration. The possibility that space-time is not what we think it is, not just incomplete in its description, not just limited in its application, but fundamentally not the bottom layer of reality, not the foundation, something that emerges, something that arises, something that appears at large scales and moderate energies to be a smooth geometric fabric, but is in fact the large-scale behavior of something deeper, something that does not look like space or time at all. That possibility is where we go next. 0947, Claude responded. There is a particular kind of vertigo that has nothing to do with height. There is a particular kind of vertigo that has nothing to do with height. It comes not from standing at the edge of a physical drop, but from standing at the edge of a conceptual one. From the moment when a framework you have relied upon, a way of organizing reality that felt so fundamental, it seemed beyond question, begins to show signs that it might not be the foundation after all, that it might be resting on something else, something you cannot see, cannot name, and have not yet found the tools to examine. This is the vertigo that awaits anyone who follows the puzzles of fundamental physics far enough, because at a certain point the evidence stops pointing toward a missing piece within our current picture of spacetime. It starts pointing toward the possibility that spacetime itself is the piece that needs to be explained, not the explainer, the explained. This is not a fringe position. It is not the speculation of theorists who have wandered too far from experimental constraint. It is the direction toward which some of the most careful, mathematically rigorous work in fundamental physics has been pointing for several decades. And to understand why, you need to sit with a distinction that sounds simple but carries enormous weight. The distinction between something that is fundamental and something that is emergent. A thing is fundamental if it cannot be derived from anything simpler. If it is a basic ingredient of reality, present at the deepest level, not reducible to the behavior of something else. A thing is emergent if it arises from the collective behavior of more basic components, if it is real and observable and causally effective, but is ultimately the large-scale expression of something operating at a deeper level. Temperature is emergent. It is a real property of physical systems. You can measure it. You can build devices that respond to it. You can describe it mathematically. But temperature is not fundamental. It does not exist at the level of individual molecules. It arises from the statistical behavior of large numbers of molecules in motion. A single molecule does not have a temperature. 1 trillion molecules collectively do. Temperature is real and emergent simultaneously. These are not contradictory properties. The question now being seriously asked about spacetime is whether it belongs in this second category. Whether the smooth curved four-dimensional geometry that Einstein gave us, the geometry that bends around black holes and stretches with cosmic expansion and slows time near massive objects, is not the bedrock of physical reality, but rather the large-scale collective behavior of something more fundamental that does not itself look like space or time. Whether space-time, like temperature, is real and emergent simultaneously. The first serious hint that this might be the case came not from cosmology or particle physics, but from a surprising direction, from the study of black holes. In the early 1970s, 4 physicists, Jacob Bekenstein, Stephen Hawking, Brandon Carter, and James Bardeen, discovered something extraordinary. Black holes obey laws that are mathematically identical to the laws of thermodynamics. The 4 laws of black hole mechanics correspond with precise mathematical equivalence to the 4 laws of thermodynamics. The surface area of a black hole's event horizon behaves like entropy. It always increases, just as thermodynamic entropy always increases. The surface gravity of a black hole behaves like temperature. The mass behaves like energy. These were not loose analogies. They were precise mathematical correspondences. Bekenstein argued that this was not a coincidence, that black holes must have genuine thermodynamic entropy proportional to the area of their event horizon. Hawking's subsequent calculation of black hole radiation confirmed that black holes have genuine temperature. The thermodynamic behavior was real, not metaphorical. But if black holes have entropy, and if that entropy is proportional to the area of the event horizon rather than the volume of the black hole, something very strange follows. In ordinary thermodynamics, the entropy of a system, the amount of information required to fully specify its microscopic state, scales with its volume. A box twice as large contains twice as many molecules and therefore roughly twice as much entropy. But black hole entropy scales with area, not volume. A black hole twice as large in radius has 4 times the surface area and therefore 4 times the entropy, not 8 times as volume scaling would suggest. The information content of a black hole is written on its surface, not in its interior. This is deeply counterintuitive. It suggests that the 3-dimensional interior of a black hole can be fully described by information encoded on its 2-dimensional boundary, 1 fewer dimension than you would expect. This observation became one of the seeds of what is now called the holographic principle. The principle, developed and formalized in the 1990s by Gerard 't Hooft and Leonard Susskind, proposes that in any region of space, the maximum amount of information that can be encoded within that region is proportional not to its volume, but to the area of its boundary. The 3-dimensional world in this picture is in some sense a projection of information encoded on a 2-dimensional surface. Not a literal hologram in the sense of a projected image, but a situation in which the full description of the physics inside a volume is encoded on its boundary, the way a hologram encodes a 3-dimensional image on a 2-dimensional surface. This would mean that one of the 3 spatial dimensions we experience is in some precise mathematical sense redundant. It is not independently real at the deepest level. It emerges from the information structure of the boundary. The holographic principle remained a suggestive but speculative idea until 1997, when Juan Maldacena published what became one of the most cited papers in the history of theoretical physics. Maldacena demonstrated a precise mathematical correspondence now called the ADS, CFT correspondence, or more generally gauge, gravity duality between two completely different types of theory. On one side, a theory of gravity in a particular curved spacetime called anti-de Sitter space, a space with a specific negative curvature that is useful for theoretical calculations but does not directly describe our universe. On the other side, a quantum field theory living on the boundary of that spacetime with no gravity at all. Maldacena showed that these two theories are exactly equivalent. Every calculation you can perform in one has a corresponding calculation in the other. Every physical situation described by the gravitational theory corresponds to a physical situation described by the boundary quantum theory, and vice versa. The two descriptions are different languages for the same reality. The implications are staggering, because one of those descriptions contains gravity in spacetime, a full geometric description of a curved universe, and the other contains no gravity and no spacetime in the conventional sense, only quantum fields on a fixed, lower-dimensional boundary. If the two descriptions are exactly equivalent, then the spacetime of the gravitational theory is not independently fundamental. It is a derived quantity. It emerges from the quantum field theory on the boundary. The geometry, the curvature, the distances, the causal structure arises from the behavior of quantum fields that do not themselves live in that geometry. Space-time in this picture is something the quantum theory produces, not something the quantum theory lives inside. This is the conceptual leap. Space-time is not the stage, it is the performance. It is what you see when a quantum system of sufficient complexity is described from a certain perspective. The geometry is real as temperature is real, but like temperature, it is not fundamental. It is emergent. It arises from something deeper that does not itself look geometric. And here, a specific candidate for that deeper, something begins to emerge from the mathematics: quantum entanglement. In 2010, Mark van Ramsdonk published a paper initially rejected by several journals before eventually achieving enormous influence, in which he argued that the geometry of spacetime is built from quantum entanglement. The argument went like this: in the ADS CFT correspondence, you can study what happens when you take a region of the boundary quantum theory and examine how entangled it is with the rest of the boundary system. When you do this, you find that the amount of entanglement between different regions of the boundary corresponds directly to geometric properties of the spacetime in the interior. Specifically, it corresponds to the connectivity of the spacetime. Regions of the boundary that are highly entangled correspond to regions of the interior spacetime that are well connected, that are nearby in the geometric sense. Regions of the boundary with low entanglement correspond to regions of the interior spacetime that are far apart or even disconnected. Van Ramsdonk took this further with a thought experiment. Imagine taking the boundary quantum system and gradually reducing the entanglement between two halves of it, disentangling them from each other. What happens to the interior spacetime? According to the mathematics, as entanglement decreases, the corresponding spacetime geometry becomes thinner, more constricted between the two regions. Continue reducing entanglement to zero, and the connection between the two halves of the spacetime pinches off entirely. The spacetime tears. Two disconnected regions remain. The geometry literally breaks apart when the entanglement disappears. The conclusion Van Ramsdonk drew was direct. Entanglement is not a property that quantum systems have within spacetime. Entanglement is what spacetime is made of. The geometric connections between different regions of space, the fact that one place is near another, the fact that spacetime is connected rather than fragmented, these are manifestations of quantum entanglement between the underlying degrees of freedom. Geometry is entanglement viewed from a certain scale. This idea has been developed considerably since Van Ramsdonk's paper. A framework called ER equals EPR, proposed by Maldacena and Susskind in 2013, suggests a deep equivalence between two apparently unrelated phenomena. Einstein-Rosen bridges the geometric structures inside black holes, connecting two regions of spacetime, also called wormholes, and Einstein-Podolsky-Rosen pairs the entangled particle pairs of quantum mechanics. The suggestion is that whenever two particles are entangled, they are connected by a microscopic wormhole, a tiny thread of geometry woven from the entanglement between their quantum states. Two maximally entangled black holes would be connected by a traversable wormhole. Two entangled particles in a laboratory would be connected by an infinitesimal geometric link. Entanglement and geometry would be the same phenomenon described in two different languages. Space itself would be the large-scale result of an enormous network of entanglement connections between microscopic quantum degrees of freedom. Distance would be a measure of how weakly two regions are entangled. Connectivity would be a measure of how strongly. The smooth geometry of general relativity, the rubber sheet, the curved fabric, the landscape that bends around stars and closes in on itself inside black holes, would be the macroscopic average behavior of a network of quantum correlations operating at scales far below anything we can currently observe. If this picture is correct, and it remains a picture, a direction, a mathematical framework that has not yet been fully developed into a complete testable theory, then spacetime is, to the quantum world, what temperature is to molecular motion: real, measurable, causally effective, but not fundamental. Not the bottom layer, not the thing from which everything else is built. Rather, the thing that is built collectively and statistically from something that does not itself look like space or time at all. And this resolves, at least in principle, some of the deepest puzzles we have encountered. If space-time is emergent, then the conflict between general relativity and quantum mechanics is not a conflict between two equally fundamental theories. It is a conflict between an emergent description and the underlying theory from which that description emerges. General relativity describes the geometry accurately at large scales. Quantum mechanics describes the underlying degrees of freedom. They appear incompatible because they operate at different levels of description, the way thermodynamics and molecular dynamics appear to use different languages because they describe the same system at different scales. A unified theory would not be a merger of two equals. It would be a quantum theory of the underlying degrees of freedom from which space-time geometry emerges as a collective behavior. General relativity would be the thermodynamics of space-time. Quantum mechanics, specifically quantum information and entanglement, would be the statistical mechanics. This would also illuminate the black hole information paradox. If space-time is built from entanglement, then the interior of a black hole is not a region sealed off from the outside universe by an impenetrable geometric boundary. It is a region whose entanglement structure with the outside is extremely complex but not severed. The information carried by infalling matter does not disappear. It becomes encoded in the entanglement structure of the Hawking radiation scrambled beyond any practical recovery, but present in principle, preserved by the unitarity of the underlying quantum evolution. The paradox dissolves, not because we find a new mechanism within space-time for information to escape, but because we recognize that the geometric picture of space-time, with its sharp event horizons and sealed interiors, is an approximation that breaks down precisely when information questions are asked. The underlying quantum reality preserves the information because the underlying quantum reality does not have a sealed interior. It has an entanglement structure, and entanglement is never truly severed. None of this is proven. Let that be said clearly and without qualification. The ADS CFT correspondence is an exact mathematical result in a theoretical setting that does not directly describe our universe. Extending it to a universe with a positive cosmological constant, the universe we actually inhabit, remains an open problem. The ER equals EPR conjecture, while mathematically suggestive and conceptually compelling, has not been fully established. The idea that space-time is emergent from entanglement is a direction, not a destination. It is a map, with many blank regions still to be filled, but it is a map, and it is more detailed, more internally consistent, and more explanatorily powerful than anything that came before it. It points toward a picture in which the geometry of the universe is not the foundation of physical reality, but a consequence of it, in which the familiar dimensions of space and the flowing arrow of time are large-scale patterns in a quantum tapestry woven from entanglement, in which the deepest truth about the universe is not written in the language of geometry, but in the language of information. You began this exploration standing inside a structure you could not see, a structure with no color, no sound, no surface to press your hand against, a structure so fundamental that everything you have ever experienced has happened within it. And now, at the far edge of what physics currently knows, that structure begins to look different, not less real, not illusory, but contingent, constructed, arising from something that does not share its properties, the way a wave arises from water molecules that are not themselves waves, the way a thought arises from neurons that are not themselves thinking. Spacetime is real, and spacetime may not be fundamental. Both of these things can be true simultaneously. And sitting with both of them at once, without resolving the tension, without forcing a premature conclusion, is perhaps the most honest response available to anyone standing at the current edge of human knowledge. There is one more thing to consider, one final turn in the road. 0950, Claude responded. There is something quietly extraordinary about the position humanity currently occupies. There is something quietly extraordinary about the position humanity currently occupies. Not in the grandiose sense, not the self-congratulatory story of a species that has conquered nature and decoded the cosmos. Something more humble than that, and more interesting. We are a collection of beings made from the debris of exploded stars, assembled by billions of years of blind evolutionary process on a small rocky planet, orbiting an unremarkable star in the outer regions of an average galaxy, one of perhaps 2 trillion galaxies in the observable universe. We have been here in our current form for an eye blink of cosmic time. Our entire recorded history occupies less than 1/10,000th of the age of the universe. And yet, and this is the part that deserves to be held carefully, we have figured out that space-time bends. We have measured the slowing of clocks near massive objects. We have detected ripples in the geometry of the universe, produced by black holes colliding a billion light-years away. We have discovered that the universe is 95% composed of things we cannot see or identify. We have found that the 2 best theories we have ever built, tested to extraordinary precision, cannot be reconciled. And we are now seriously entertaining the possibility that the very stage on which the universe performs is not fundamental, that space and time emerge from something deeper, something written in the language of quantum information and entanglement. All of this from a species that has been doing science for a few centuries. All of this from inside the thing we are trying to understand. That is not a small thing. That is in fact one of the most remarkable things that has ever happened in this universe as far as we know. But the story is not finished. The map has edges, and at those edges several paths lead forward, not toward a single destination, but toward different possible versions of what a complete theory might look like. None of them is proven, none of them is complete. Each of them captures something real, illuminates something important, and fails somewhere that the others do not. Together they represent the current frontier. The places where the best minds working on the deepest questions have planted their flags, knowing that the flags may need to be moved. One of the oldest and most developed approaches is string theory. The central idea is that the fundamental constituents of nature are not point-like particles, but tiny one-dimensional vibrating object strings. Different vibrational modes of the same string correspond to different particles. An electron is a string vibrating one way, a photon is a string vibrating another way. And crucially, this was the discovery that made string theory genuinely compelling, rather than merely speculative. One of the vibrational modes of a closed string behaves exactly like a graviton, the hypothetical quantum carrier of gravitationnelle interaction. String theory, in other words, automatically includes gravity. It produces a quantum theory in which gravity emerges naturally from the same framework that describes all other forces and particles. This was the first theoretical framework to achieve this, without producing the uncontrollable infinities that plagued earlier attempts. The infinities that appeared when you tried to quantize gravity as a point-particle field theory simply did not appear when gravity was described as a mode of a vibrating string. The extended nature of the string smeared out the interactions that caused the infinities, eliminating them before they could form. String theory makes other predictions. It requires extra dimensions, not the 4 dimensions of space-time we experience, but 10 or 11 in its most developed versions. The additional dimensions are proposed to be compactified, curled up at scales so small that they are invisible to any instrument we currently possess. The specific way these extra dimensions are curled determines the physical constants of the universe, the masses of particles, the strengths of forces, the value of the cosmological constant. But the number of distinct ways the extra dimensions can be curled is staggering. Estimates suggest there may be something like 10 to the power of 500 distinct configurations, each corresponding to a different universe with different physical laws. This vast landscape of possible universes has been both a source of theoretical richness and a source of deep criticism. If almost any set of physical constants is realizable within string theory, then string theory makes almost no specific predictions about the constants of our universe. It cannot tell you why the electron has the mass it has, or why the cosmological constant has the value it has. The theory contains our universe somewhere within its landscape of possibilities, but it cannot identify which possibility we occupy or explain why. String theory has also, despite decades of development and the contributions of thousands of researchers, produced no confirmed experimental prediction that distinguishes it from other theories. It operates at energy scales so far beyond current experimental reach that direct testing may not be possible for centuries, if it is possible at all. This does not make it wrong. It makes it, in the strict empirical sense, unconfirmed, a mathematically extraordinarily rich framework that has produced genuine insights, including the ADS, CFT correspondence, which is one of string theory's most important results, but has not yet made the transition from theoretical structure to tested physical theory. A very different approach is taken by loop quantum gravity, where string theory begins by modifying the fundamental objects of physics. Replacing point particles with strings. Loop quantum gravity begins by taking general relativity seriously as a quantum theory and attempting to quantize it directly without adding new dimensions or new fundamental objects. The result is a picture in which space itself is granular at the smallest scales, not continuous, but composed of discrete, finite units, loops woven into a network called a spin network. The smooth geometry of general relativity emerges from these networks as an approximation, valid at large scales, breaking down at the Planck scale, where the discrete structure becomes apparent. Time in loop quantum gravity is also discrete. It advances in finite steps rather than flowing continuously. The theory avoids the infinities of standard quantum gravity attempts because the granularity of spacetime provides a natural cutoff. There is a smallest possible volume, a smallest possible area below which the concept of distance ceases to have meaning. The infinities that appear when you try to probe arbitrarily small scales never arise because there are no arbitrarily small scales. Space itself has a minimum grain. Loop quantum gravity has achieved genuine results. It has produced a coherent picture of the quantum geometry of space. It has shown that the Big Bang singularity can be resolved, that tracing the universe back through the Big Bang leads not to a mathematical catastrophe, but to a previous contracting phase, a big bounce from which the current expansion emerged. It has made predictions about the fine structure of the cosmic microwave background that future experiments might test. But it has struggled to incorporate the other forces of nature, where string theory naturally unifies gravity with electromagnetism, and the nuclear forces. Loop quantum gravity focuses on gravity alone and has not yet found a natural way to include the standard model of particle physics. It describes the quantum geometry of spacetime without yet providing a complete picture of the matter and energy that inhabit that geometry. Causal set theory takes yet another direction. It proposes that the fundamental structure of spacetime is not a continuous manifold or a network of loops, but simply a collection of discrete events ordered by causality. The causal relations which events can influence which other events are all there is. Spacetime geometry emerges from the statistical behavior of large numbers of causally ordered events, the way fluid dynamics emerges from the statistical behavior of large numbers of molecules. The smooth manifold of general relativity is the macroscopic description. The causal set is the microscopic reality. Causal set theory has the virtue of conceptual simplicity. It requires no extra dimensions, no exotic new objects, no elaborate mathematical structures beyond the ordering relation itself. It has made one remarkable prediction that the value of the cosmological constant, the quantity associated with dark energy, should be small but non-zero. A prediction made before the 1998 discovery that the cosmological constant is indeed small but non-zero. Whether this constitutes a genuine predictive success or a fortunate coincidence remains debated, but it is at minimum suggestive. Then there are approaches that do not even begin with spacetime. Amplitude-hedron research developed by Nima Arkani Hamed and collaborators has found that the probabilities of particle interactions, quantities called scattering amplitudes, can be computed from the geometry of a mathematical object called the amplitude-hedron without any reference to spacetime or locality. The calculation that would require thousands of terms using conventional Feynman diagram methods collapses to a simple geometric calculation involving the amplitude-hedron's volume. Spacetime and locality are not inputs to this calculation. They emerge from it as consequences of the geometry of an abstract mathematical space. This suggests that there may exist a formulation of fundamental physics in which spacetime does not appear at the foundational level at all, in which it is a derived quantity, a feature of a more abstract mathematical structure that is itself the true foundation. The amplitude-hedron approach is not yet a complete theory. It has been developed mainly for a specific, highly symmetric version of quantum field theory. But the direction it points is consistent with the broader suggestion from holography and entanglement that spacetime is emergent, that the foundation is informational or geometric in an abstract sense, and that the familiar dimensions of space and time are large-scale consequences rather than fundamental ingredients. What all of these approaches share, what makes the current moment in fundamental physics genuinely distinctive, is that they are all in their different ways questioning the foundational status of space-time, not denying its reality, not proposing that space and time are illusions, but seriously, mathematically, rigorously exploring the possibility that space-time is what shows up when you look at something deeper from a sufficient distance, that the smooth, curved geometry of general relativity is the long wavelength limit of a quantum theory of something that does not itself look geometric. That distance and duration are measures of relationships, entanglement, causality, information, rather than properties of an independently existing fabric. This is not where physics was 100 years ago or 50 years ago or even 30 years ago. It is a genuinely new direction, and the fact that multiple independent lines of research, black hole thermodynamics, holography, ADS, CFT, entanglement and geometry, causal sets, amplitude-hedra, are all pointing in the same general direction is not proof. But it is not nothing either. It is the kind of convergence that in the history of science has sometimes preceded a breakthrough. What the breakthrough will look like, no one can say. The history of fundamental physics offers little comfort to those who want to predict the shape of the next revolution. Quantum mechanics did not look like an extension of classical mechanics. It looked like something from another world: probability, waves, uncertainty, principles, superpositions of states, the collapse of the wave function. General relativity did not look like an improvement on Newtonian gravity. It looked like a replacement of the entire conceptual framework, a rewriting of what space-time and gravity fundamentally are. If a unified theory of quantum gravity is discovered, a theory that contains both general relativity and quantum mechanics as special cases, that resolves the information paradox, that explains the values of the physical constants, that identifies the nature of dark matter and dark energy, it will almost certainly not look like either of its predecessors. It will require new concepts, new mathematical structures, new ways of thinking about what a physical theory is supposed to describe. It may require abandoning intuitions so deeply embedded in the current framework that we do not yet know we have them. The history of physics is a history of discovering that what seemed obviously true was only approximately true, that what seemed like the foundation was only a flaw above a deeper flaw, that the familiar is not the fundamental, And this brings us back to where we began. To you sitting inside something, you cannot see something with no color and no sound and no surface to press your hand against. Something that bends around every massive object in the universe. Something that slowed the ticking of a clock on a satellite this morning, that bent the path of light from a star 1 billion years ago, that stretched and compressed as 2 black holes merged and sent ripples across the cosmos that were detected by instruments sensitive enough to measure a change in distance smaller than 1/10,000th the width of a proton. You are inside space-time. You have always been inside space-time. Every moment of your existence has unfolded within its geometry, and we do not know what it is. We know that it bends, we know that it stretches, we know that it responds to mass and energy with a precision described by Einstein's equations to better accuracy than any other theory in the history of science. We know that it slows time and guides the paths of planets and closes in on itself inside black holes. We know that at its extremes, it contradicts the other framework we rely on to describe reality, producing paradoxes that neither theory can resolve. We know that its thermodynamic behavior near black holes suggests it has a microscopic structure we have not identified. We know that its geometry may be built from quantum entanglement, that its dimensions may be emergent rather than fundamental, that the smooth fabric we experience may be the large-scale average of something that does not itself look like space or time at all. We know all of this, and we do not know what space-time is. Sit with that for a moment, not with frustration, not with the anxious desire to resolve it, but with something closer to wonder. Because this is the condition that has always preceded the deepest advances in human understanding. Not the confident state of those who believe they are close to the final answer, but the honest, uncomfortable, exhilarating state of those who have pushed far enough to see clearly how much remains unknown. Copernicus did not know what the planets were made of. Newton did not know what gravity was at its root. Einstein did not know what space-time was made of. They worked at the edge of what was knowable, using the tools available to them, and what they found was not the end of the story, but a deeper version of the question. That is the nature of the enterprise. Not a march toward a final resting place, but an asymptotic approach to something that keeps receding, revealing new depth at every scale, offering new questions in place of every answer. You are here, in this moment, on this small planet, inside this structure that bends and stretches, and may not be fundamental, looking outward at a universe that is 95% unknown to us, backward at a history in which every framework that seemed final was eventually superseded, and forward at a frontier where some of the most careful thinkers alive are seriously entertaining the possibility that space itself is woven from entanglement, that the distance between 2 points is a measure of how deeply connected they are in a quantum sense, that the geometry of the cosmos is an entanglement expression of information, that what we call reality is the large-scale behavior of something so far below our current reach that we do not yet have a name for it. This is not a comfortable position, but it is an honest one, and honesty at the frontier of knowledge is its own kind of shelter, because it means we are not pretending. It means the questions are real. It means the universe is genuinely stranger than we thought, which has always in every era of science turned out to be true. And it means that whatever comes next, whatever theory eventually stitches the large and the small together, whatever mathematical structure eventually reveals what space-time is made of or what it emerges from, it will be discovered by minds that are willing to stand at the edge of what is known and look outward without flinching. Minds that have made peace with the vastness of what remains unknown. Minds that have learned, as you perhaps have learned in the course of this exploration, that not understanding something fully is not a failure. It is the beginning. The universe does not owe us simplicity. It does not owe us a picture that fits comfortably within the cognitive architecture of a primate on a small planet. What it offers instead is something rarer and more valuable. A structure so deep, so intricate, so far beyond the reach of ordinary intuition, that every generation of those who study it carefully enough is left with a greater sense of mystery than the one before, not less mystery. More. Each answer opens into a larger question. Each framework reveals its own edges. Each confirmation of a theory is also, if you look carefully enough, a pointer toward the next thing the theory cannot explain. You live inside space-time. You are made of it, in a sense. The atoms that constitute your body move through it, age within it, are bound together by forces that propagate through it. The light that allows you to see carries information about the curvature of the space-time it has traveled through. The gravity that holds you to the surface of this planet is the geometry of space-time curving inward toward Earth's center. The moments that pass as you read these words are the ticking of a clock embedded in a structure that bends differently, depending on where in the universe that clock happens to sit. You are not separate from space-time. You are an event within it. A brief, improbable, extraordinarily specific arrangement of matter and energy that has persisted long enough to wonder about the nature of the thing it is arranged within. And somewhere in a laboratory or a library or a quiet room at an unusual hour, someone is working on the next step, adding a line to an equation, noticing a pattern in data that does not quite fit, asking a question that no one has formulated in quite that way before. Following the logic of a deeply uncomfortable idea to its conclusion, the way a young patent clerk in Bern once followed the logic of a fixed speed of light to a conclusion that restructured everything. The next step is not known, but the direction is becoming clearer. And the fact that we can see the direction at all that we have pushed far enough to know where the edges are, to name the specific places where our understanding fails to identify the questions that matter most, is itself a kind of extraordinary achievement. A candle in an enormous darkness, small, flickering, but burning. The darkness has not changed. It stretches in every direction farther than light has traveled since the beginning of time, but the candle is real, and the light it casts, however small, is ours.